Merci, Eric. Although I'm the RC manager of this project, Scott Dallimore is leading the onshore work, and I'm leading the offshore work. So I'll be presenting you some of the highlights that happened over the past fiscal year, and more specifically between October and March for this project. So I'm going to move my, okay. If you look at the figure on the right, you could see that permafrost covers approximately 50% of the Canadian landmass. And obviously, with global climate warming, permafrost degrades. And when it degrades, well, it releases a full suite of contaminants, including greenhouse gases, heavy metals. And our project is focusing on looking at first the degradation process of the permafrost, and also what's coming out of it and how it affects the environment. So here's the partners of this project. I won't go into the details, obviously, but just to say that 70% of the project participants are external collaborators. And the GSC staff involved in this project, well, most of them are not devoted 100% to this project in particular, maybe just a few of them. So we're very lucky to have collaborators involved in this project. Bit of context, if you look on the figure on the left, that's the projected increase over the Arctic by 2090, and also you have the study area that is indicated on that figure. What you can see also is the retreat from the actual limit of the permafrost from between now and 2090. So obviously with that, the retreat of the limit, permafrost conditions are going to change. And if you look at the sketch on the left, it triggers a full suite of processes that are mostly similar onshore and offshore, and that's what we're studying. And we're more specifically looking at the release of methane from degrading permafrost and also mercury. So terrestrial permafrost highlights. Last field season, we had a successful field season onshore, and two things happened during that fieldwork period. First of all, we were there to with St. Francis Xavier University to ground truth some of the hotspots that were detected by atmospheric methane measurements made by airborne surveys. So the figure on the left, on the right, sorry, shows you those hotspots, and also you could look at the different sites where direct measurements were made on the ground. And you could see that if you look a little bit closer at the isotopic ratios, you can see that those methane sources show different types of methane. So going from thermogenic, biogenic, and mixed methane sources. We also did successfully recover osmosis samplers that were deployed in lakes for more than 2 years. That allowed us to record seasonal and pluriannual fluctuations of methane fluxes. And those samples are currently being analyzed at the University of Maryland. And well, it should be part of the next fiscal year highlight the results. So that's the second item we focused on for the terrestrial work. Shifting to the subsea permafrost degradation. So with Polytechnique, we've been using a vast data set of seismic data to develop different methods that allow us to to detect remotely changing permafrost condition. This is an example using seismic velocity that is a good proxy to identify changes in permafrost conditions. So we're using looking at the data set in different domains using a deep neural network, and we can better picture the permafrost body, and more specifically is seismic velocities that I told you was related to changing conditions. We also, using differential mapping, we're mapping seafloor changes associated with permafrost degradation. This is one example showing differential mapping between 2010 and 2019. You can see that there's quite a change over even a short period of 9 years. And one of these holes that that has been detected at the outer shelf of the Northwest Territories, you can see that even the White House could be easily fitted in. So we're going to go back this fall, and we're going to ground truth these sites, do more mapping, and try to collect some samples that could provide us some cues on what is coming out of those holes in terms of fluid and contaminants. One other thing we're doing at the GSC is looking at the structural evolution of the basin, and more specifically at shallow faulting, and looking at evidence of fluid leakage from these faults, which might be impacting the permafrost condition at its base, especially if you have warm fluids that provides heat at the base of the permafrost. We're looking for any indications, seismic indications that could tell us more about the impact of fluid leakage at the bottom of the permafrost. Lab measurements, we're doing some experiments, real-time continuous measurements on degrading permafrost samples using simultaneous electrical, acoustic, and CT measurements. So what you see on the left is our lab apparatus that was custom made. And on the right, that's an example of what we're recording. So you can see at the top the acoustic signal that changes with the changing permafrost conditions, so as the permafrost is melting. Obviously, this is important for us to better appraise what's happening on geophysical data recorded in the field. And what you have at the bottom are image segmentation that documents changes of state recorded as the permafrost is melting. We also do numerical simulation of heat transfer, and we try to better assess the impact of geological structures on permafrost degradation using well logs that are available to us. So that's work in progress. Obviously, that ties in with the work that is done by the GC on structural interpretation of seismic data. And that's my contact. If you have any questions, I'll be glad to answer them in French or English.